Hi everyone, in today's video we are going to start our next chapter by talking about sequences. So in this video you are going to learn to identify patterns of arithmetic and geometric sequences. Then we're going to use those patterns to figure out a rule for a sequence. And then you're going to use that rule to find terms that come later in the sequence. So let's go ahead and get started with some vocabulary. So first, a sequence is just a list of numbers. So the list of numbers, the list of integers in particular, are going to be, they're not always integers, I'm going to take that back. The list of numbers are going to be the range, and we're going to call the domain just the first number in the list, the second number in the list, the third number in the list. So when you're looking at a sequence of numbers, you're technically looking at the range of the function. So there are a couple of different types of sequences. The first thing that I want to point out today is that we have finite sequences, which means we're looking at a list of numbers that stops. In this finite sequence that you're given as an example, there are four terms in the list. It stops after the fourth term. An infinite sequence is one that keeps going on forever and ever. And you'll see that that is denoted by the ellipse, that's the three dots, that comes at the end of the sequence of numbers. Now, what we're going to be working a lot on today is figuring out for a given list of numbers, a given sequence, an equation that will be the rule for that. So if our list of numbers, if we're looking at this finite sequence, for example, is 2, 4, 6, 8, then the rule that's being followed there is that we are adding 2. 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8. So the pattern that that one is following is going to help us to create an equation so then we can find any number in a list of an infinite sequence that we want. So there's some vocab that we're going to work with. Let's go ahead and get into finding some terms in a sequence. So in this first example, you are going to find the first 6 terms in the sequence. So I'm going to draw my squiggly bracket, and there are going to be 6 numbers in this list. I'm going to find those 6 numbers by using a sub n. This is our rule equation. So in all of these sequences that we're looking at, you're going to notice that an n is used a lot. The n is from the domain. It is the which one in the list are we talking about right now. So if I say a sub 1, that means I want the first number in the list. It means that I'm going to take that 1, and because of this rule that I'm given, I'm plugging in the domain where the n is, and then simplifying it. So the first number in our list is 3. To find the second number in our list, that's a sub 2. I'm plugging in the 2 to our rule. I'm simplifying it. And that's the second number in our list. Now we can obviously just keep right on going. To find the third number in our list, that means we're looking for a sub 3. I'm going to take the 3 and plug it in for the rule. That gives me my next number. For a sub 4, I'm plugging in 4. That gives me my fourth number in the list. I'm going all the way to 6, so I'm going to do a sub 5 and a sub 6. So that's 5 to the third power plus 2, which is 125 plus 2. And 6 to the third power plus 2 is 216 plus 2. All right, so it was a whole lot of plugging and chugging, but I found the first 6 terms in my sequence given the a sub n rule of n to the third plus 2. So this list of numbers, that's my answer. Okay, so the first kind of sequence that we're going to talk about is called a recursive sequence. And what this is, it means that you have to use the previous number in the sequence to find the next number in the sequence. So in the example that we just did, it was not recursive because if I wanted to just go ahead and find the 15th number in the sequence, then I would just plug that 15 into the rule and then simplify to whatever that great big number is. With recursive sequences, you can't jump around like that. So let's look at the notation here. I know ace of 1 is equal to 1. That means that the first number in my list, if I'm again trying to find the first 6 terms, I know that ace of 1, the first number in the list, is 1. Now look at our rule here. Our rule says 3 times ace of n minus 1. So when I'm looking for ace of 2, I'm going to plug that 2 in still. I've got 3 times ace of, and my n was 2, so I'm going to plug in 2 minus 1 in the subscript there. So that subscript is ace of 2 minus 1 is 1. That means then I need to substitute in ace of 1 to this spot in order to find what ace of 2 is. I need to do 3 times ace of 1, and I just got told ace of 1 is 1, and that gives me ace of 2. Now when I find ace of 3, I'm going to plug in my rule. The n goes where the n is in the rule. Look what happens here. 3 minus 1 is 2, and now I need to plug in ace of 2, which I just found up here. I need to substitute there in order to continue simplifying. So I'm going to substitute that in, and that gives me ace of 3. To find ace of 4, I'm doing 3 times ace of 4 minus 1, which is 3 times ace of 3. I just found the third number in the list. It's 9. So I'm going to substitute in that 9 because it's telling me to sub in the third number in the list. That means ace of 4, or our fourth number in the list, is 27. And again, we're trying to get those first 6 terms, so I'm going to keep right on going with this. I'm going to do 5 minus 1, which is ace of 4. So that means this 27, because that is ace of 4, gets substituted in for that fourth number in the list. That gives me my fifth number of 81, and I still have to do ace of 6 as well. 3 times ace of 6 minus 1 is 3 times ace of 5. Ace of 5 I just found out was equal to 81, so I'm going to substitute that in. 3 times 81, and that's going to be a nice big number. It's going to be 243. All right. So notice in recursive sequences, and that means that you're going to have a rule that has an n minus 1 in the subscript of the domain of the list. That means you're going to have to find the previous one and go back and plug it in. We can't just say ace of 15 is equal to blah. We have to start at the beginning of the list. Okay, so the next thing that we need to talk about, the next type of sequence, is that we are going to talk about 2 different special patterns, arithmetic sequences and geometric sequences. An arithmetic sequence is one that has what's called a common difference. And all that means is that you are going to be adding or subtracting the same amount every time to get the next number in the list. And whatever that pattern is, we're going to say D is equal to that pattern. So if we look at this first list of numbers, if we are trying to add to get from -4 to 1, we have to add 5. Then to get from 1 to 6, we have to add 5 again, and then we add 5 again, and then we add 5 again. So we have a consistent pattern where the pattern is D is 5, meaning we're adding 5 each time. So that means that yes, this is an arithmetic sequence because it follows that same pattern all the way through. The second one, let's look at it. To get from 3 to 5, we're adding 2. But to get from 5 to 9, that's plus 4. And then to get from 9 to 15, that's plus 6. This is a d value that is changing over time. It's not always the same thing being added. So that means no, this one is not an arithmetic sequence because it doesn't follow that constant pattern. So let's look at some places where we might use arithmetic sequences. We have in this next section at the top, the arithmetic sequence formula, and this is going to be something that is super important for you to have memorized. We're going to use it often. Notice in the formula, to find any term in the list, a sub n, you need to know a sub 1, which is the first term in your list. You also need to know which term you're trying to find, the first term, the 15th term, the 20th term, and you need to know the pattern. So let's see if we can look through a couple of these. The first example here says write a rule, so I need to figure out what the equation is. That's what I'm using the formula for the nth term of a sequence. So I'm trying to find the rule, and then I'm going to find a sub 15, the 15th number in the list. I'm going to use the rule for that. I'm not just going to keep adding whatever it is until I get to 15. Because if I asked you to find a sub 100, nobody wants to do that. Like 99 times, right? Okay, so let's figure out what the rule is first. To get from -7 to -10, I am adding a -3 or subtracting 3. And that keeps happening. The D, the pattern, is -3 for this one. So let's plug in what we know to find our rule, and we are going to have to simplify this. We want it to be in standard form. The formula says that we need a sub 1. Well, we know a sub 1. That's the first term in the list. It's -7. Then we don't have an n yet because we want to find a rule that we can use for anything. So we're going to leave the n there. But we do know, and this is multiplication here, we do know that d is -3. We just found that out. So now we're just going to use Algebra 1 to simplify. That means then that we're going to distribute. And then we're going to combine our like terms. This standard form is our rule. So now, if we have this sequence of numbers and we want to find any other number in the list, we don't have to keep subtracting 3 each time. We can just plug into the rule. So if I want to find a sub 15, that means I'm going to use my rule, but I'm going to put the 15, because that's what n is equal to, into that spot. And then I'm just going to simplify. So for this one, when I plug in 15, I get -49 as the 15th number in the list. All right, so let's look at another one. This time we're given something a little different. We're asked to write a rule again, given a term and a common difference. So this time we've been told what the pattern is. We've been told that the 27th number in the list is 263. We're just trying to figure out what the rule is. We don't have to find a number in the list. So we're going to use that formula. We know a sub n is 263, right? Because we know the 27th. So when n is 27, a sub n is 263. We haven't been told what the first term is in the list, so I'm going to leave that part of the formula as a sub 1. We've been told the 27th term, so that means we know 27 is what n is equal to when we're looking at a sub 27. And then we also know what d is. So again, I'm going to use Algebra 1 to simplify this. This time I'm solving for a sub 1. So I'm going to do 26 times 11, it looks like, which is 286. And then I'm going to subtract 286 from both sides. And that gives me a sub 1 is equal to -23. So remember, my directions were not find the first term in the list. My directions were find the rule. And in order to find the rule, that means I need to plug into the formula and I have to know a sub 1. So now let's go back to our formula and set up a rule for anything that follows this pattern. We know a sub 1 is negative 23, and we know the pattern is 11. So we can simplify this to put it in standard form, and that will give us our rule because now we know the first term in the list. So 11n minus 34 is our rule. We could find any number in the list now when all we were given is a number in the list and the rule that was followed. All right, so the next thing that I want to do is a different kind of sequence, but one that is kind of similar. In addition to arithmetic sequences, we're going to have geometric sequences. And geometric sequences, their pattern is called a constant ratio. And what that means is that we're going to be multiplying for our pattern, and it's going to be by the same thing every time when we multiply. So let's see. This first one, ooh, those are big numbers. So I'm actually going to start in the middle. That's okay to do. We can go back and check the beginning. So I know that 25, in order to get to 5, you have to divide by 5, right? 25 divided by 5 equals 5. So that means then that I'm multiplying by 1 over 5, because I can do 25 over 1 times 1/5 using our fractions to get that 25 over 5 and get there. So what I want to see now is if I do the rest of these, am I also dividing by 5 or multiplying by 1/5? And we are going to always write our patterns for geometric sequences as multiplication. Okay, so we're multiplying by 1 over 5. We are not writing this as dividing by 5. We got to write it as a fraction if it's division. So if I keep going, 5 times 1/5, or 5 divided by 5, is 1, so that works. If I go back to my beginning, 625 times 1/5 is 125, and 125 times 1/5 is 25. So that pattern is working. So we're going to use the variable r here and say r is 1/5. Yes, this is a geometric sequence because it has a constant pattern of multiplying by 1/5. Okay, let's look at this next one. To get from the first number in the list to the second, if we're multiplying, it has to be by 2. But then to get from 2 to 6, that's multiplying by 3. And to get from 6 to 24, that's multiplying by 4. So we don't have a constant rate that we're multiplying by. So no, this is not geometric because it doesn't have a constant ratio that's being used. Okay, so let's get to the formula now for these. We again have a formula. This is one that you need to have memorized. We're going to use it often. Notice that there are a lot of similarities in the formula in terms of pieces of information. You need to know a sub 1, which is the first term in the list. You need to know r, which is what we just found out. That's the pattern. And remember, n is just which number in the list we're talking about. So our first example in this section says write the rule. So we're going to be finding a sub n here. We're going to figure out the rule and put it in standard form. And then find a sub 7. So we want to find the 7th number in the list without having to just keep multiplying on and on and on. So first thing we need to do is figure out what the pattern is. 3 times what will get us to 12? Well, that's going to be times 4. Let's make sure that still works. Does 12 times 4 equal 48? It does. And that pattern's being followed all the way through. So I know that r in this one is 4. So let's put together our information to use the formula. A sub n is equal to a sub 1, that's the first number in your list, 3, times the ratio r, so that's 4, and then it's raised to the power n minus 1. Now here's the great news about geometric sequences. This is in standard form. You are not going to multiply together these two bases because this one has an exponent and this one has an exponent of 1. The bases are not the same, so you cannot do that using our exponent rules. Geometric sequence rules are super easy because you just plug in what you know. You don't have to simplify them at all. All right, so now with that, let's find a sub 7. Remember, 7 is what n is equal to. So we're going to have 3 times 4 raised to the 7 minus 1, using that rule we just created. Now for this, I'm going to follow order of operations and do my exponent first. I'm not going to multiply together 3 times 4. So I'm going to do 7 minus 1 is 6, and then 4 to the 6th power is the next thing that I need to simplify. 4 to the 6th power is 4,096, and then I multiply that number by 3, so my final answer is 12,288. That's a really big number in that list, isn't it? Okay, the last thing we're going to do is another example for geometric sequences that has a little difference in it. So this time we are writing a rule for the nth term. So we're going to write our rule. We're given our list of numbers, so let's go ahead and figure out our pattern. To get from 2 to 6, we're multiplying by 3, and that keeps happening all the way through, so that means r is going to be 3. And then we're going to determine whether the given sequence is arithmetic or geometric. Well, we just answered that, right? Because how did we get from 2 to 6? We multiplied by 3, and we kept multiplying by 3, and that worked for the whole list. So that means this one's geometric. It is not arithmetic because we're not adding by something. And then we also need to find ace of 10. So we've answered the geometric question about the type of sequence. Now let's write our rule. So we're going to do ace of n. And the formula for geometric sequences says you write your first term in the list, ace of 1, that's 2. You multiply it by the ratio, that's 3, but that ratio is raised to the n minus 1 power. So that's my rule. And now I'm going to find ace of 10, meaning I'm going to plug the 10 in for n. 2 times 3 raised to the 10 minus 1. Order of operations says deal with that exponent first. So that's going to be 3 to the 9th power, and I want to do that part next. So that's going to be 2 times 19,683. And when I multiply 2 times that big number, I'm going to get a doubly big number, 39,366. And that is my 10th number in that sequence that follows a geometric pattern. Okay, so in this video, you learned how to identify the pattern of arithmetic and geometric sequences, and then once we knew the pattern, we figured out the rule for them using the formula, and then found a term later in the sequence using that rule. Go ahead and try the Now You Try problems.